Hello, everyone. I'm Debanjali Chatterjee, a PhD student at the Energy and Transport Sciences Lab at Purdue University and president of the ECS Purdue Student Chapter. Welcome back to our fall webinar series on solid-state batteries and electrochemistry. So our student chapter comprises of over 20 student members led by the chapter officers under the guidance of the chapter advisory board. Professor Partha Mukherjee from the School of Mechanical Engineering at Purdue is our lead faculty advisor. We have Dr. Judy Jeevarajan, Vice President of Research at Underwriters Labs as our distinguished industry advisor, Professor Rebecca Chase from the School of Mechanical Engineering, and Professor Julia Laskin from the Department of Chemistry at Purdue are our co-faculty advisors. In spring 2021, we conducted our signature webinar series on women in electrochemical sciences and engineering, which was exceptionally well received and appreciated in the scientific community. Inspired by its success, this semester, we have launched a webinar series on one of the hot topics in energy storage research, solid-state batteries and electrochemistry. Today, our speaker is Dr. Steve Harris from Lawrence Berkeley National Lab. Steve received a BS degree in chemistry from UCLA and a PhD in physical chemistry from Harvard University. After a Miller postdoctoral fellowship at UC Berkeley, he began his career at the General Motors Research Labs. Apart from a stint at the Ford Scientific Research Labs, he worked at GM until 2011 when he was awarded a Miller visiting professorship in the UC Berkeley Chemistry Department. Since then, he has worked in the Materials Science and Energy Storage divisions at Lawrence Berkeley National Lab. During that time, he has also been a visiting scholar in the Materials Science and Engineering Department at Stanford, has consulted for battery companies, private equity companies, and venture capital companies. He is also on the advisory boards of several battery startups. Steve's work has ranged widely, and it includes studies of combustion chemistry, the kinetics and thermodynamics for growth of CVD films, aerosol dynamics modeling, fatigue failure in gears, and fracture mechanics in cast aluminum. When he returned to GM from Ford, he started work on lithium-ion batteries, focusing on how the presence of heterogeneities and flaws affects ion transport, durability, and energy density. He is presently looking at the mechanics and electrochemistry at lithium metal interfaces for solid-state batteries, and he has recently proposed a general solution to the problem of dendrite penetration through solid electrolytes. Today, he will be speaking on lithium contact mechanics and preventing dendrite penetration into solid electrolytes. Steve, we look forward to your talk.
Thank you. So do you see my screen and hear me?
Not right now.
Wait a minute. Share, oh, sorry. There.
Yes,
okay.
Yes, perfect, yes.
And you still hear me?
Yes.
Yes, perfect.
Amazing.
Thank you, Steve.
Okay, so I'm going to talk about contact mechanics, and I'm also going to talk about preventing dendrite penetration into solid electrolytes. So to start with, I'm going to have two goals in this talk. The first goal is to understand and predict how the interfacial impedance or resistance is affected by pressure and time, and this is the interface between a solid electrolyte and lithium metal. And my collaborators are Xin Zhang, Jane Wong, Katie Harrison, and Scott Roberts. And the second part of my talk, I'm going to propose a general solution to the dendrite penetration problem in solid electrolytes. And my collaborators here are Yuqi and Chunmei Ban. So let's start with how do we deal with the interfacial resistance between a solid electrolyte and lithium metal. So let's start with the question, how does the battery field think about the nature of solid-solid contact? And it comes back to a paper by Monroe and Newman in 2003, where they said the way to prevent dendrites is to suppress them mechanically. And this is a figure from their paper. You've got lithium metal. In their paper, this is a solid polymer separator. And there's a boundary condition coming in from above where lithium ions enter this fixed volume, which might be 10 by 10 microns. And the lithium metal starts off with some random protrusion or protodendrite. And there's going to be a competition for whether the lithium deposits at the tip here, which will grow the dendrite, or whether it deposits out in the wings, in which case the surface is flattened. And one conclusion that they came to is that the flattening requires a high shear modulus, high for a polymer, of several gigapascals at least. It's interesting that their analysis doesn't mention yield strength of lithium at all. Now, this sort of architecture is pretty much universally used by everybody who thinks about or models dendrite penetration, in that you have lithium in perfect conformal contact with a solid electrolyte, just like here. So I mentioned yield strength, and in my work, yield strength is a critical parameter. There's a couple of different kinds of yield strength you can think about. One is the yield strength in tension. Another is the indentation yield strength, which tends to be about 3 times higher, and it's called the hardness. It's higher because in order to make lithium go plastic during indentation, the displaced lithiums have to push against the bulk, so you need to push harder. So imagine that you're a lithium metal and a solid electrolyte is approaching you. That solid electrolyte has asperities or bumps on the surface, and those asperities are going to push into you and make you go plastic. So if you're lithium, the parameter that controls whether you go plastic is the hardness. The local pressure is always going to be less than the hardness, because if it tries to get to the hardness, the lithium is just going to flow. So, but if the external pressure ever actually reaches the hardness, then the pressure will flow. So then the lithium will flow so that the pressure is equal to the hardness everywhere. At that point, contact is conformal. And also at that point, the interfacial resistance is minimized because it's in contact everywhere. And it's also independent of pressure, because pressing harder doesn't get you better contact once you're conformal. But contact between real solids is actually complex, and it's because engineering surfaces are always rough at the micron or submicron scale. And so in the real world, pretty much conformal contact never happens if you just bring real surfaces together in contact. And I'm going to show you a couple of cartoons to try and convince you of that. Here I have 2 ideal, perfectly flat parallel surfaces, and I'm bringing them together under a stack pressure of 1 atmosphere. And when you bring them together, indeed, you get perfect conformal contact, and the pressure everywhere is 1 atmosphere. But if you think about a real surface, then when you bring real surfaces together, initially they contact just at the peaks of the tallest disparities. The pressure at those contact points can get very high. It can go up to, say, the yield strength of the material. And so let's imagine a case where the yield strength of this material is 100 times greater than the stack pressure. If you have a situation like this, then the entire load is going to be carried by just 1% of the surface. And so you never approach anywhere near like conformal contact. And this is the sort of contact situation that you have in many real life situations. And so what this means is that these pictures that are used either in Newman's model or here in Klinsmann's, where you are examining what goes on in a single dendrite, that's perfectly fine, but these are not representative volume elements. And so you can't make a real interface from replicates of these. If you want to do a real surface, you need to consider places where there is no contact. So what we decided to do is to build a model that would predict the evolution of impedance. And of course, impedance is going to be related to the contact situation you have. And we're going to look at evolution in space and time. And the model is going to have information about contact, plastic deformation. We're assuming perfectly elastic, perfectly plastic. And it'll also cover creep plating and stripping. The mechanical properties are going to be taken from Dasgupta, University of Michigan, with one exception that I'll mention in a minute. And it's also going to, as I mentioned, it's going to consider creep. Creep is really important. Creep is is what happens if you push on a material below the yield strength and you get permanent deformation, nevertheless. And lithium creeps. So you push on it even relatively gently, and it's gradually going to flow. And this flow can move over large distances, in our case, let's say hundreds of microns from where you initially contact. And the creep just continues. There's nothing to stop it. And so it can go on for days for example. What this means is that our model is going to have to cover a very wide dynamic range, running from milliseconds to tens of hours and from tens of nanometers to hundreds of microns. To do this in 3D and in time is with a spatial resolution required on the order of a micron, excuse me, would be extremely difficult if you wanted to use finite element. And so the contact mechanics field has moved to a fast Fourier transform approach to do this, which is extremely fast, although there's approximations you need to make, of course. So let me talk a little bit about some of the details of this model that you have to think about. The first thing is contact, and there's actually a difference between electrical contact and mechanical contact. On the left, I'm representing an asperity on the solid electrolyte with this blue cone, and it's indenting the red lithium, and it makes this indentation. And for electrical contact, the contact area that's relevant is the complete contact area of this sort of partial cone in this region, because the current flows over this entire surface of this little conical region. And so we have the relevant area we'll call the true contact area. But mechanical contact is different. In mechanical contact, the load is going to be supported by the lithium in this projected area. And so if you think about hardness, this is the principle behind measuring hardness. You're dividing the load by the projected contact area. Now, of course, these contact areas are related, and for any given surface, you might have something like the mean, the average of the mean cosine angle or something that might be more complex. But in general, these numbers are proportional to each other, but they're not the same thing. Now, I mentioned that we're using this FFT technique, and there are some drawbacks that you get when you try and take advantage of the enormous speed up. One of those drawbacks is that it's valid when theta is very small. And also, when you indent lithium, where does that lithium go? It piles up on the edges around here. This FFT approach ignores that, and so it doesn't conserve lithium. So, those are potentially very significant drawbacks, penalties that you have to pay in order to get the speed. Now, I also have to think about how resistance is related to the contact area. And there's this relationship which you can think of as defining the area-specific resistance, ASR. ASR is an intrinsic property of a particular interface in that it is independent of the contact area. So it has units of ohm square centimeters. If you divide ASR by the true contact area, you get the resistance that you actually measure. So now I want to consider a hypothetical case where you bring a solid electrolyte against lithium metal, and we're going to consider the case where all the deformation is plastic. So here is a representation of that. We have a contact stress map. The color tells you the surface normal stress. And at every point, the local pressure is either zero, blue, which means it's not in contact at all, or it's red, which means it's at the hardness value of 3 times the tensile yield strength. Now, in a case like this, if you double the stack pressure, you have to double the contact area. And that's because since all the contact is at the same pressure, you need double the area in order to support double the load. So based on that, we can replace the area of contact in this equation by the interfacial, by pressure. And so now we conclude that the interfacial resistance has to scale like 1 over the pressure. And this is an interesting relationship. It's very general. For example, it has nothing to do with the surface roughness profile as long as all deformation is plastic. So let's see whether that actually happens. Remember, we've decided that if all contact is plastic, then the interfacial resistance should scale like 1 over the pressure. So here's some data from Jürgen Janik's group, and the black dots represent the interfacial resistance that he measured as a function of stack pressure. And so what I did is I took the data off his graph and replotted it as the log of the interfacial resistance against the log of the pressure. And that gives a pretty straight line with a slope pretty close to -1. By the way, this is the only right way to do this. If you just plot the resistance against the square root of pressure things, it gives you a straight line no matter what this exponent is. So, you need to take logs of this data. Anyway, so what we see is that the interfacial resistance scales like 1 over pressure, which means that in this case where it's LLZO, all the deformation is indeed plastic, just like we hypothesized in a particular case. The other thing that's quite interesting in this data is that as you get to 40 megapascals, the interfacial resistance is still decreasing, which means that the contact area is still decreasing at 40 megapascals. It's not fully conformal yet, which means in turn that the hardness has to be greater than 40 megapascals, or the effective yield strength has to be at least 14 megapascals. Now, if you're uncomfortable with the idea of thinking that the hardness of lithium can be 40 megapascals, here's some data from Matt Farr. It's nano indentation data, where he's measuring the hardness as a function of the size of the indentation. And what we see here is a very large size effect. Size effect is sort of universal. This is a pretty steep one. And so down where the indentation is down at submicron level, you get a 40 megapascal hardness. What this means is that this data here, where the interfacial resistance is still falling at 40, and Farr's data, these data are perfectly consistent as long as to the lithium, the solid electrolyte looks like a bunch of submicron indenters, and that's not hard to believe. Now, because of this fact that the yield strength varies so much with the size of the indentation, and we expect all different sizes in a realistic solid electrolyte, we're going to treat the effective yield strength as an adjustable parameter in this model. Interestingly, the contact area scales with pressure we showed. Now, if conformal contact requires 40 megapascals, that means if you're at 4 atmospheres, you only have 1% contact. So when you think about contact between lithium and a solid electrolyte under bodice pressures, it's almost all not in contact. Now, that data was for LLZO. Here's some data from Shirley Meng's lab looking at LPS chloride. And up to 15 megapascals, I again took her data and we plotted it on a log-log plot. We get a very nice straight line with a slope again of -1. So in this case, again, all deformation is plastic for both very hard and less hard solid electrolytes. Now, creep is another factor that we have to take into account, and there's creep laws that are sort of empirical that you can look up in books. So this is the uniaxial creep rate, and and it's the strain rate that you get from tensile tests that are done in the lab, such as those done at Michigan. Sigma, which can depend on local position X and Y, is the uniaxial stress. M is some sort of stress, empirical stress exponent, and Q is an activation energy. And again, this is coming from Dasgupta. However, you can't really use this sort of thing if you're thinking about indentation. And that's because indentation creep requires higher load than uniaxial creep. And that's for the same sort of reason. Now, if you're indenting, the displaced lithium has to push against lithium that's already there. So the creep rate is going to be slower for the same force. And so empirically, it turns out that there's a constant that involves the yield strength that can relate these two. And so when we put in all the constants, we get that the indentation creep is some function of this ratio of the yields of the local contact stress and the local yield stress. And that's raised to the 6.6 power. That's Dasgupta's number. And other people have gotten very similar numbers. Now, what this means is, this is a very, very large exponent. What that means is as the local stress drops for whatever reason, the creep rate there is going to drastically slow down. It also means that the creep rate is extremely sensitive to what value you use for the yield strength. And this is going to turn out to be very helpful for us, because it turns out if you double the yield strength, then all the calculation goes bananas, and so it's going to severely limit the value of the yield strength that we can choose, given that we're using as an adjustable parameter. So this shows a little bit like what creep-induced evolution of the contact area looks like. Initially, you might have very high stresses, so you have very fast creep, but and so the contact might look like this. After an hour, the creep has redistributed where the lithium is. It's redistributed the load toward more conformal contact, and therefore the stress locally is going to go down, and therefore the creep rate is going to fall drastically. Here it is after 5 hours, and what you can see is that the stress at one location can affect the stress at distant locations and at much later times, which is why you need long times and large regions if you're going to understand the mechanics of lithium. So anyway, we built this model, and we decided to apply it to some symmetric cell data that Jeff Sakamoto had just reported on. Here's his symmetric cell. It's got lithium electrodes and some LLZO solid electrolyte in between. The experiment is run entirely in mode where he's stripping from the right side and plating from the left side, and he's got adjustable stack pressures shown in red. And then he can measure the voltage drop across this region. The voltage drop that he measures is going to be equal to the voltage drop across this interface. That's this R sub IF we talked about. And that voltage drop is just going to be the current times that interfacial resistance, plus all the other voltage drops in his system, which we're going to treat as constant. So remember, this interfacial resistance looks like the area-specific resistance divided by the true contact area, which might change. So here is his data. The red data is on the right, and it shows how he varies the stack pressure. He starts out at 2 megapascals, and over 10 hours drops it to 1, and then brings it back up to 2, and then he has 4 cycles like this. And then simultaneously, in the black data, he's measuring the voltage drop across here. So we start out, and initially we're lowering the stress. Now, if you lower the pressure, the contact is going to get worse. The true contact area is going to go down. This elastic energy is going to push these things apart. So A true goes down, which means this term gets larger and the voltage drop goes up. And then when he starts increasing the pressure, the true contact area is going to get larger. So this whole term is going to get smaller, and the voltage drop that he measures is going to go down. And then he repeats that 4 times. Now, what you notice is that the amplitude of this oscillation is getting smaller. We ascribe this to creep, because what's creep doing? As time goes on, creep is bringing you closer towards conformal contact. And remember, at conformal contact, pressure is irrelevant. And so you expect the effective pressure to get lower as creep improves the contact area. So this graph shows our prediction, or our model, in red against his data in black. And we used, as I said, the yield strength as an adjustable parameter. Now, we wanted to look at the sensitivity of the yield strength in terms of how sensitive our fit was to its value. So we looked at the standard deviation between the Sakamoto's data in black and our prediction in red, and we compared that standard deviation to values that we chose for the yield strength. And what we saw is, over a very narrow range of yield strength values that we chose, we got good fit. But as soon as you got above about 18 megapascals, the fit got terrible, and there was just nothing we could do to get a decent fit. And so in order to make Sakamoto's data, put it in harmony with our model, we need a yield strength below 18. Now, you may remember a few slides ago that I said in order for Yannick's data to make any sense at all, the yield strength had to be at least 14. And then just in the last few months, Julia Greer published some data where she measured the yield strength to be 16 megapascals. And so we are sort of getting to a consensus of what the effective yield strength is. Remember, effective means that the yield strength can vary from point to point, but it's acting as though the overall yield strength were very close to 16. So now what I want to do is propose a general solution. This is part 2 of my talk, a general solution to the problem of penetration of dendrites into solid electrolytes. And so the goal of solid electrolytes is to combine them with lithium metal, and the benefits are widespread. For example, perhaps the lithium metal is not too chemically reactive with a solid electrolyte, in which case we can that would allow us to use lithium metal as the anode, and lithium takes up a lot less space and weight than the lithiated graphite that we're using now, so we get an increase in energy density. And then there's other things that we could hope for. For example, since the solid electrolytes tend to be ceramic, or at least quite hard, certainly compared to lithium metal, we should expect that dendrites should be blocked. These dendrites are really fingers of lithium that can grow through a conventional separator and cause short circuits and fire. So we should hope that that doesn't happen. There's a number of barriers to actually implementing these solid state electrolytes. One is that what I just talked about is that there's generally going to be poor solid-solid contact between the solid electrolyte and lithium, which means you can have high internal interfacial resistances, which can also change with time, even when you have fairly high pressures. And then the other problem, which was a real disappointment, is that lithium still causes short circuits, which might be surprising because of how soft lithium is. Well, in a way, it shouldn't be surprising because there are other examples in material science where soft materials penetrate through hard materials without much of a problem. Stress corrosion cracking is one example. But I want to propose a solution to this. By the way, here is what a all solid state battery might look like at some sort of scale. So here are the current collectors. Here's the lithium metal. We have an all solid state separator. And then we have a cathode, which is made of these green cathode particles. And in the pores, we are filling them with the solid electrolyte. Okay, so how do we propose a solution, or how do we solve this dendrite penetration problem? And the number of solutions proposed is equal to the number of people in the field. Everybody thinks their solution is best. So I can tell you without any doubt, my solution is in fact the best solution. So here's my idea. In order for dendrites to penetrate through solid electrolytes, there has to be a fracture in the solid electrolyte. It's not going to just push its way through by brute force. That's not the way ceramics break. So I'm saying you need the solid electrolyte to fracture. And so if you want to stop dendrite penetration, the right approach, in my view, is to increase the fracture toughness of the solid electrolyte. So fracture toughness is a parameter that effectively measures how readily is a material willing to grow a crack from a small crack to a large crack. And so if something is got a very high fracture toughness, then you're just not going to be able to put cracks in the thing, and therefore, in my picture, dendrites simply won't penetrate it. So it turns out that if you want to increase the fracture toughness of anything, metals, ceramics, glasses, there's some pretty standard industry techniques for doing this. And one of them is you simply put the surface of the material into a state of residual compressive stress. I've underlined this word residual because I've discovered that a lot of people misinterpret it to have something to do with stack pressure or external forces. The residual stress in the material is the stress that remains after you've unloaded it, after there are no more outside forces. So it's acting like it's a material property. And what it really is it's just a property of how the atoms in the material are arranged. So if you've got compressive stress, that means the atoms are just overcrowded. They're pushing up against each other. If you have residual tensile stress, that means the atoms are farther apart than they want to be and the bonds are stretched. Okay, so imagine we have very high compressive stress. If you have high enough compressive stress, then the cracks that exist can't propagate, or if they don't exist, they can't form, or if they pre-exist, they're going to close. And that's because you've got all these atoms that are pushing against each other. And it turns out that you can put residual compressive stresses into ceramics that approach 10 gigapascals. That's a gigantic number. It's strong enough to tear atoms out of molecules. It's many orders of magnitude higher than what you could get in any reasonable kind of external load. And so these kinds of compressive stress basically can overwhelm any other forces in the system. And so the idea is, well, if you have such high compressive stresses, cracks can't form, they can't propagate, and pre-existing cracks will close. So there's a number of ways that people can put these residual compressive stresses into the surface of materials. One of them is called ion exchange. So let's say you have glass, it's got lots of sodium ions that are small. Suppose you can exchange the sodium ions for potassium ions that are larger. Well, if everything else stays the same, then the atoms are now crowded. And so you've got compressive stress. And this is how Gorilla Glass is made. So if you have a cell phone, the glass is crack resistant. And what they mean by crack resistant is they've put a residual compressive stress into its surface with potassium. Another approach is ion implantation. And here you put a material into a vacuum and you accelerate ions to very, very high kinetic energy. It can be hundreds of kilovolts, even megavolts. The ions bury themselves into the surface and thereby increase the crowdedness of the atoms in the surface and give you very high compressive stresses. So you might ask, well, if the compressive stress is so high, then how is lithium going to move around? The atoms are crowded, we just said. And so that's a fair question. So my colleague Yu Chi did some molecular dynamics calculations in LLZO and just said, well, what happens to the diffusivity of lithium if you introduce overcrowding or undercrowding in this lattice? And so she took the stress level from 30 gigapascal compressive to 15 tensile. These are ridiculous levels, but in a computer, you can do anything. And so she did the calculation at 1100 Kelvin because that speeds up the process, and then extrapolated it down to either 300 Kelvin, shown as open circles, or 350 Kelvin, shown as these dots. And the experimental measurements of diffusivity are all done on this scale, right, at zero stress, and between 305 and 339 Kelvin. And as you can see, the prediction is quite accurate. The take-home message is that in the range where it's plausible compressive stresses, the compressive stresses lead to only a very modest reduction in the diffusivity of lithium. So this shouldn't be a showstopper. So the next step is to actually try it out, excuse me, and see if it works. So these are preliminary experiments done in Chunmei Ban's lab. And what she did is she took a pellet of LLZO or maybe LLZTO, and she implanted part of it with fluoride ions and left part of it pristine. And then made symmetric cells where she runs the lithium either through the pristine parts or through the implanted parts. And so what she sees is that in the pristine system, these are, by the way, on two different timescales. In the pristine system, she can get ohmic behavior up to about 0.3 milliamps per square centimeter, after which it goes unstable, and then above 1.2 milliamps per square centimeter, she gets a short circuit. In the implanted region, she gets ohmic behavior up to 4 times higher, up to 1.2 milliamps per square centimeter before it goes unstable, and then you don't get a short circuit until 3.5 milliamps per square centimeter, 2 to 3 times higher than the pristine. So directionally, this works. If you look at the cross-section of these solid electrolytes, in the pristine case, you can see it brightly lit up where lithium is penetrating. And if you zoom in, you can see these dendrites all over the place. Whereas in the implanted system, you see no evidence of any lithium dendrites at all. So to summarize my talk, there were two parts. In the first part, I said that we were going to build a three-dimensional multi-scale time-dependent model of a lithium metal solid electrolyte interface. And we incorporated contact, the difference between electrical and mechanical contact, elastic plastic deformation. We're assuming perfect elastic, perfectly plastic. We incorporated creep, plating, stripping, and we used all of the mechanical properties taken from Michigan, except yield strength. And what we found is that we can get a simultaneous fit to our model and to Yannick's data, Sakamoto's data, and Greer's data if we assign an effective yield strength of close to 16 megapascals for the lithium. The main learning we got is that it's really creep that controls when and where current flows. So if you have contact at a particular point, that's where the current is flowing. And 5 hours later and 30 microns away, the lithium may have flowed into a new place, and now you have a new contact, and that's where the current is going to flow. And so the calculations we claim have to cover thousands of square microns and tens of hours if you're going to be realistic. If you're looking at just one dendrite, you're not looking at a representative volume element. The second part of the talk was about dendrite penetration, and our panacea, the way we think you're going to solve this in general, is you increase the fracture toughness of the solid electrolyte with high residual compressive stresses. And the idea is that this inhibits fracture pathways for dendrites. If there's no crack, the dendrite can't go anywhere. Even if you build up hydrostatic pressures within the lithium that's close to a gigapascal, which is possible with modest overpotentials, with realistic overpotentials, even those kinds of pressures can be overwhelmed by residual compressive stresses that you can impose. And the evidence we have so far is that we see no dendrite penetration beneath ion implanted regions. In addition to reducing dendrite penetration, there are other potential side benefits for introducing high residual compressive stress. In the first place, these materials are extremely brittle, and it's a challenge. It's going to be a challenge to handle them in a factory environment. Of course, if they have improved fracture toughness, then they don't break as often. The other idea is that if you're doing implantation, you tend to amorphize the surface, and amorphous surfaces often may have fewer flaws and therefore be less reactive, and that may make it less important to have, for example, chemical interlayers. So that's the end of the technical talk. And the last 3 minutes, I'm going to talk about a totally different subject. So I spent most of my career at General Motors and Ford. And then now I'm at a national lab. I, of course, did my graduate and postdoc at academic environments. So I've seen a lot of different kinds of job environments. And I made a presentation on what's the difference between academic and industrial research jobs. If you're interested, it's about a 35-minute talk with about an hour and a half of Q&A. And you can access it. I put it on YouTube. And so if you get this deck, you can access that if you're interested. But in the meantime, I'll just tell you, these are the topics that I covered in that presentation. The idea is that, what are the differences? Well, obviously tenure is a big difference. The reason that you get hired is different in academia and in industry. Measures of success are different. The importance and the value of collaborations are very different. In order to succeed, you need very different kinds of political skills. The challenges for bringing a new technology to market are very different. The way your employer rewards you is different. How research groups are run, how you get funded is different, which projects you work on. Technical communication is totally different. Problem complexity is very different. In universities, you tend to work on model problems. In industry, you tend to work on much more complex problems. What if you want to change jobs? What are you going to be doing in 10 years? And how do you think about industry-academic collaborations? These are all important questions that I think everybody should ask themselves. I think you can have a great career in industry, you can have a great career in academia, you can have a great career in national labs, but it might be that you personally would feel better and fit in better with one of these others. So I'll stop there. Thank you very much.